All right, now we're looking at number 12 for the study guide. Two ladders are leaning against a wall. The same angle is shown. How many feet up the wall does the shorter ladder reach? So we're looking, if we look at the ladder, the ground, and the wall forming a triangle, we're looking for the length of this leg here of a right triangle. Okay, the wall and the ground they intersect at right angles. All right, and then notice here too that you've got, this angle here is congruent to this angle here. So we know that these two triangles that the ladder, wall, and ground form are similar triangles, okay? Because remember we had a postulate that said if two angles in one triangle are congruent to two angles in another triangle, then the triangles are similar. All right, so we know these triangles are similar. That means that we can set up a proportion with ratios of corresponding sides and solve for the unknown, which is, I'll put an H for height. We're looking for H. So let's find a pair of corresponding sides where we know the length of each, and that would be the ladder lengths, the hypotenuses. So that I'm going to set up a ratio, 60 over 24. Has to equal, this side corresponds with the unknown side, so that's 45 over H. So we cross multiply and divide, and we get what? Looking to see, I already did this. Let's see here, number 12. I don't see number 12. So we have, let's see, 24 times 45 divided by 60, and we get 18. So the height of the wall that the ladder's reaching is 18 feet. H is equal to 18 feet. Let's move on to number 13. Number 13, which of the following can be used to prove that triangle ABC is congruent to triangle DEF? All right, we're looking at right triangles, and typically when you're dealing with right triangles, the first theorem that you want to look at for showing that right triangles are congruent is the hypotenuse leg theorem. But we don't see that our hypotenuses are congruent, so we have to move on to something else. I see that this side's congruent to this side, this angle with this angle, and this side with this side. Okay, so we have side, angle, side, side, angle, side. So the side, angle, side theorem shows that these two triangles are congruent. Just the same order that it's written is the same order that the leg lengths or the side lengths and the angles are given or viewed. Side, angle, side, side, angle, side. Okay, number 14. Write a proof about the figure shown below. So we have a triangle WXZ. We have this point X going to Z. And we're told in the proof below, Nancy started with the fact that XZ is perpendicular to bisector, is a perpendicular bisector of WY. And proved that triangle, I guess that should be triangle WYZ is an isosceles triangle. Okay, so she has a flow proof going here. She's starting with a given segment XZ is a perpendicular bisector of WY. And that means that WX is congruent to YX. Okay, by definition of a bisector, which XZ is. And that also means that the measures of angle 1 and angle 2 are 90 degrees. Well, she also stated that XZ is congruent to XZ, it's congruent to itself by the reflexive property. So from all that, we can conclude that triangle WXZ is congruent to WX or to YXZ. Why is that? There's the question mark. Why is that? So through all this, we showed that WX is congruent to XY, and then we've got right angles, and then we showed that this side is congruent to itself. So again, we see the side angle side theorem demonstrated here. So that would be C. And then let's go ahead and look at the rest of the proof. Remember, she's trying to prove that that this is an isosceles triangle. So if WZ, if these two triangles are congruent, then WZ is congruent to ZY, okay? Because corresponding parts of congruent triangles are congruent, all right? So that means, and so what we see here is these two legs are congruent, so that means this WXY or WYZ is an isosceles triangle.